We're all trying to figure out one of the biggest mysteries out there, dark matter. But what if we've been looking for the wrong thing this whole time? Forget about particles for a second. Today we're hunting something, well, a lot stranger. Think of it like a cosmic ghost, a massive, invisible wall just stretching through space.
So, let's just jump right in with the big question. We always hear about dark matter as these tiny invisible particles, right? Just zipping around. But what if it's not that at all? What if it's something way more fundamental, almost like a glitch, a flaw in the actual fabric of space-time, left over from the very beginning?
All right, to even wrap our heads around how a dark matter wall could be a real thing, we've got to rewind. I'm talking way, way back to the first tiny fractions of a second after the Big Bang. We need to explore how these cosmic glitches, or as physicists call them, topological defects, could have even formed in the first place.
Okay, so this is the key idea right here, a topological defect. It sounds complicated, but think of it this way. It's basically a leftover from something called a phase transition way back in the early universe. It's like a scar that got left behind when the universe cooled down and the laws of physics themselves kinda settled into place. And these things aren't just nothing. They're real structures packed with a ton of energy.
So, what's a phase transition? Honestly, the best way to picture it is something we see all the time. Imagine the early universe as this incredibly hot, uniform soup of energy. And as it expanded and cooled, it started to freeze into the universe we know today. It's really just like water turning into ice. But how does that freezing actually happen, in a physics sense? Well, take a look at this shape. Physicists call it a Mexican hat potential. It shows the energy of a fundamental field. When the universe was super hot, that cosmic soup, the field was balanced right at the top, on that peak. But as things cooled down, it had to roll down and settle into a low-energy state. And that's anywhere along the bottom rim of the hat. Now here's the crucial part. There's no single right spot for it to land.
And this is where the walls come from. Just picture it. This freezing is happening everywhere across the universe at the same time. So in one patch of space, the field might roll down and settle on, say, the left side of the brim. But in a totally different region, one that's too far away to have talked to the first one yet, it settles on the right side. So what happens where these two different regions of space-time bump into each other? A boundary forms, and that boundary is what we call a domain wall.
So there you have it, a way to actually make these gigantic cosmic walls. Pretty cool, right? A brand new idea for what dark matter could be. But, hold on, not so fast. Because for decades, this whole idea came with a massive, potentially universe-breaking problem for cosmologists.
And I'm not exaggerating. Look at this quote, a cosmic catastrophe. This wasn't some minor little issue. The thinking was, if these walls were stable and just hung around, our universe, well, it just wouldn't look like it does. It might not even exist at all. The stakes here are as high as they get.
And this giant headache actually has a name, the domain wall problem. It's really the central conflict of this whole story. It's the reason why, for a long time, most physicists just wrote these things off as impossible.
This table really shows you the problem in a nutshell. Look, as the universe gets bigger, everything in it gets spread out, right? Its energy density goes down. Radiation, you can see, thins out super fast. Matter, both normal and dark, a little slower. But then look at stable domain walls. They barely dilute at all. As the universe expands, their energy density just kind of hangs around. And that creates a massive problem. And the consequences of that are just huge. If these walls were stable, that stubborn energy of theirs would have quickly just taken over. They would have completely dominated everything else in the universe. We'd be living in a lumpy, chaotic, violently expanding cosmos, which is nothing like the one we see. So for a long time, the conclusion was simple. Stable, giant walls, impossible.
Okay, so if huge, stable walls are a cosmic no-go, that seems like the end of the story. But what if they aren't stable? What if they're smaller and they just pass through? Could that be dark matter? And how in the world would you even look for something like that? Well, the answer turned out to be incredibly clever. It wasn't about building something new, but about repurposing something we all use literally every single day.
So, meet the biggest dark matter detector ever created. And it's not buried a mile underground in some lab. Nope. It's orbiting right over our heads, right now. Scientists had this brilliant idea. The entire constellation of GPS satellites, with all those super precise atomic clocks on board, could basically act as a planet-sized net, a 50,000 kilometer wide net to be exact, to catch these cosmic ghosts.
So here's the genius of it. Imagine one of these domain walls just sweeping through our solar system at hundreds of kilometers per second. As it passes over a GPS satellite, its bizarre physics would ever so slightly mess with the fundamental constants of nature right inside that satellite's atomic clock. This would create a tiny temporary glitch, a little hiccup in its timing signal. So if you see a very specific pattern of these little glitches rippling through one satellite, then the next, you've just seen a domain wall go by.
Okay, so the setup is perfect. You've got this incredible planet-sized detector. You have a super specific signal you're hunting for. A team of researchers dove into years and years of GPS data looking for exactly that signature. The big question is, what did they find?
And let me tell you, this was no small task. They dug through a whopping 16 years of archival data. We're talking about all the high-precision timing information from the entire GPS network, all of it, just searching for that one telltale pattern of glitches. And after all that searching, after sifting through all that data, the number of dark matter walls they detected was 0. Now I know what you're thinking. 0? That's it? What a letdown. But hang on. In science, especially when you're hunting for something as mysterious as dark matter, finding nothing can actually be everything. It can be one of the most important results you could hope for. Why? Because by not finding anything, these researchers were able to say with a lot of confidence what isn't out there. They could rule out a huge chunk of possibilities for what these walls could be like. This result sets the strongest limits we've ever had on how this type of dark matter can interact with normal matter. So yeah, they didn't find the ghost, but what they did was make the room it has to hide in a lot smaller. And every time we do that, we get one step closer to figuring out what the heck the rest of our universe is actually made of.
So where does a big result like this leave us? Does it mean we give up on the idea? Not at all. The hunt for the universe's missing matter is far from over. If anything, it's just getting smarter.
And the path forward is actually really clear. For one, scientists can create even better ways to analyze the data, to dig deeper into all that background noise. They can make the detector even bigger by roping in other satellite networks, like Galileo from Europe or Russia's GLONASS. And hey, why stop at walls? They can tweak the search to look for other kinds of cosmic glitches, like one-dimensional cosmic strings. Or they can use brand new networks of ultra-precise atomic clocks that are being built right here on the ground.
It's pretty amazing when you think about it. We've literally used our entire planet and its technology as a single scientific instrument. And what we've learned is that if these dark matter walls are out there, they are incredibly good at hiding. The search has gotten narrower, our tools are getting sharper, and the biggest mystery in the cosmos is still out there, just waiting for us. The only question is, where are we going to look next?